Okay. Okay. Oh, can you hear me? Yes. Okay. Okay. Hello. Hello. We are moving right along. Hello, Michelle. Hello, Christopher. Hello, Alan. Hello, Yavi. Hello, Maria. Hello, Stephanie, Shai, Katie, Michelle, Q, and Brooke, Victoria, Marilyn, Mohammed. Okay, people, we're going to get faster and faster. Good afternoon. Yes. Oh, yeah. Okay. Good afternoon, Jada. Good afternoon, Mohammed. Good afternoon, Brooke. Good afternoon, Michelle F. Good afternoon. Morning, Alan. Hello, Chris. Good afternoon, Marilyn. Afternoon, Maria, who was here for 45 minutes earlier. Anyway, good afternoon. Yeah, noticed, appreciated. Good afternoon, Shy. Good afternoon, Michelle Q. Good afternoon, Victoria, whose last name I will never get wrong again, but that's also because I will never attempt to pronounce it. Okay, at least in public. Let's just make tracks here. Excuse me. Oh, more people coming. Hold on. Hold on. Hello, Shy. Oh, hello, Shy. Okay, sorry. Now I see. Excellent. All right. And oh, weird. Wait, are you? Oh, you're doing that thing. All right. I'm not even gonna go down the rabbit hole, but yes, thank you for doing that thing, all of you. Um, oh my God. What? Okay, I'm not even gonna. I am committed to not being distracted by fun today, but that's really wow. It's like a live phone bitmoji thing. Okay. I just lost. Okay, I want to just pick up where we were, and good afternoon, Emily, if I didn't say. I just want to pick up the very last thing. I want to pick up from where we were yesterday. Like where we finished last class. Where we finished was finally, like we resolved an answer and more importantly, a general method from question 9, homework 1B, which now means that the super long homework 2 that's been like sitting around for a while is like much more dealable. I want to start showing, like, you'll start seeing how a lot of homework 2, a lot, not all, but a lot of homework 2 was like practicing this new understanding we have. Um, and even homework 3, which technically was due recently, but I think I just extended for whatever it's worth to Wednesday. Even homework 3, you'll see, is just like a practice exercise in what we now are like beginning to understand. Okay, so like the hard big breakthrough is question 9, homework 1B. Once you break through that wall, which I'm not saying everybody has yet, but once we do, then homework 2 and homework 3 fall into place a lot more comfortably. So what is it that I think we know so far? Um, okay. Oh, sorry. Okay. Well, all right, no, hold on. Sorry, I was about to jump step slightly. Hang on one second. I'm sorry. Okay, what I just wrote here in purple is a big deal. I'm going to explain it again in English, like, or I'm going to review it slightly quickly, I hope, in English. It is what we take away from the ending of homework 1, but bear with me. I'm going to quickly try to say again what I think it means, but then I'm going to generalize it. I'm going to make it I'm going to turn it into a broader statement with more broad implications. So buckle your seatbelt or something. Like, what I'm saying is, in homework 1, we had a specific piece of mass that was attached to a specific spring. The specific piece of mass had a mass of m. The specific spring had a stiffness of k, right? And the mass was initially held at. It was held initially at some displacement away from the equilibrium position that we know is x equals 0, right? So we specifically had a physical system. We had a physical mass on a physical spring stiffness k, particles mass m, right? And what we said and our goal was to figure out. Our goal was to figure out x as a function of time, of t, right? To figure out where the mass would be at any given moment in time. That was our goal. What did we know? What was the givens? The given was that the spring obeyed Hooke's law, F equals negative kx, and that all forces obeyed Newton's second law, F net equals ma, right? So we put together Hooke's law with F net equals ma, and we arrived at this second order differential equation, right? We arrived from the physics description of this physics situation. We arrived at this equation, d2x dt squared equals negative k over mx, right? We found that the second derivative of position with respect to time was directly proportional to position. We found out that the second derivative of x with respect to t was equal to a constant times -1 times the original function x itself. That didn't tell us what the original function was. It told us that if we could solve that differential equation, it told us enough information to enable us, hopefully, to solve that differential equation and come up with a description of x as a function of time. So we got this specific differential equation that related x, meaning position in space, to t, meaning time. And we found out by the end of the last class, we found out that if that differential equation was true, if this differential equation was true, then we found out that this expression for x was at least one working solution to that differential equation, right? We found a solution to the differential equation. The solution was not a number, right? The solution was not a number. The solution was a function that enabled us to get numbers, right? So again, just to remind you before we go any further, in the old days, you might be somewhat used to the idea. You might think when you're trying to solve a science problem, you're trying to solve a physics problem, you have an equation and then you use that equation to plug in numbers and solve your problem. What we're getting deeper now, and we're saying, no. Now what happens actually is if you're facing nature or you're taking data in a lab, what nature or laboratory data often presents you with is a differential equation, an equation that doesn't tell you output as related to input. It tells you some rate of change. And what we must do as physicists is solve that differential equation to actually get a regular everyday function. So our functions are solutions to differential equations. Then we plug in numbers into the function and we get out numbers and we find, like, for example, in question 9 of homework 1B, we finally, we got a function x equals x naught cosine omega t. So we were able to plug in 1 second for t. We were able to plug in 0.3 over, we were able to plug in 200 over 0.3 square rooted for omega. take the cosine of that in radians, multiply by 0.15 for x naught, and get out our final answer, x 0.116 meters, right? But again, what I'm trying to emphasize right now is what we really did there was we arrived at a differential equation that described position on a spring as a function of time spent on that spring, and we plug numbers into that final function. That, I don't know if that's like a quick review of what we did. Now, what I want to say is that's like a big deal, because we're going to use that like for the rest of the course. So I have a lot of things to say about it. Whoa, sorry. Okay. Okay. So what I'm going to say, here's how we're going to use, like the whole year, the whole semester started with like us intensely analyzing a mass going back and forth on a spring, okay, in a certain way, back and forth, a certain oscillatory fashion, for which all these things were true, like energy conservation was true, initial conditions were set, etc. What I want to say from now on is the math that we just did doesn't only apply to a specific mass on a specific spring. From now on, let's move from X to Z. Let's use Z from now on to mean any variable that you can measure and which, i.e., you can like scientifically, observe and quantify. If Z is any measurable variable which depends on time, so if from now on Z stands for any general dependent variable, like could be the position of some mass on some spring on an x-axis, or could be the angular position of some pendulum bob on a string going back and forth in an arc, right? Or could be, as in the example of homework, so that was like lab, right? Or like as in the example of homework 3, could be the amount, the temperature of some weather system at some moment in time, or could be, as this course will progress toward, could be like the magnitude of the intensity of the electric field, whatever that means, at some moment in time. If Z is anything that you can measure in time, then from now on, we're going to say if data leads us to realize that Z obeys this differential equation, this specific second order differential equation that we just, arrived at last class, if you can write that the differential equation of that form about Z. So in other words, I'm saying two things. I'm saying, number one, well, I'm saying not just if you could put Z into any differential equation, but specifically that one. that we just learned. And what do I mean by that one? I mean the one that says the second time derivative of z equals -1 times some positive constant times z itself. If z, right, which is what we said, like it happened on last class, that the constant was like k over m. But I'm saying any constant, as long as we have reason to believe that this thing that we're measuring, whether it's linear position, angular position, electric field, whatever, if this thing that we're measuring, if it's true that the second time derivative equals -1 times some constant, like some positive constant, times z itself, right? Then then we know that z oscillates harmonically in time such that, like, so first of all, I'm going to say from now on, I'm saying any variable that obeys that differential equation or can be described by that differential equation is a harmonic oscillator. In the case of our mass on the spring, like the mass went back and forth along the x-axis according to that differential equation that we didn't know when we started off the homework, but we knew by the end of question 9, that the position of that mass on the x-axis can be described by that differential equation. That means right there, from here on in, that mass is oscillating, going back and forth in a very specific manner that from now on we're going to call harmonic oscillation. I will be more explicit about that in 2 minutes. I mean, you may have been already tossing around that term in lab. From now on, any system. So, and same thing, if a pendulum's angle, theta, can be described by that differential equation, if its second time derivative is directly proportional to theta itself, then we're going to say from now on that theta is oscillating, not just going back and forth, not just oscillating, but oscillating in this very specific way that we call harmonic, right? Which, among other things, means it'll conserve energy. It'll obey all of those properties that we, looked at from questions 1 through 8 on that homework. We'll say from now on that whatever z is, if it can be described by that differential equation, then we'll know from now on that z oscillates harmonically in time such that, let me write that clear, like that's an English word, which I'll define, but what it mathematically means is this. It means that from now on, sorry, that's not supposed to be an x, it's supposed to be z. Sorry. If z obeys that differential equation, then a solution to that differential equation is z equals z naught cosine omega t, for which omega is the square root of whatever that constant was in the differential equation. Obviously, I'm going to do examples with this in a minute, but honestly, all of the homework, well, most of homework 2 and all of homework 3 is an example of this. If you see it all, I'm going to do examples, but I'm telling you right now that this is the secret to homework 3. Homework 3 looks like out of nowhere when you first look at it. It's like weather. Why are we talking about weather all of a sudden? Or temperature? Why are we talking? But this is the page that unlocks homework 3. I promise you. Of course, I'm going to explain this more. But I am saying, like in the case, say for x, in the case of homework 1, where d2x dt squared equals negative k over, okay, I'll write it down. Hold on. For the example, homework 1b, See, I'm saying, and of course I'm going to explain this more, like what all this means, but like if you look at what we concluded last class, we got to that differential equation in x's. We finally solved it. We found that the solution was x equals x naught cosine omega t. And by the way, that wasn't a joke. Like it took all class, right? Like we had to guess, we had to build up a whole conjecture, then we had to verify it. That doesn't come. I mean, that was one long class. You don't get it immediately just because we did in one class. But the notes you ever want to look at of how we did that are from that class. But again, also to practice that, that's what the first like 50 questions in homework 2 are about. We will do those. But for the moment, I'm just saying what we did was we solved that differential equation that had x's and t's in it, and we got x equals x naught cosine omega t. But what we found is omega was the square root of k over m. In other words, if you want two derivatives of that x expression to get back to the negative k over m x expression, it works as long as by omega, what you mean is the square root of k over m. What I'm trying to say right now is that this whole idea is true no matter whether you're using x's or y's or z's or thetas or whatever. And more specifically, what I'm really trying to say right now is it doesn't matter what's in the parentheses of that it doesn't matter what's in parentheses of that original differential equation, as long as what's in parentheses is a constant, and k over m is like a constant divided by a constant divided by a constant is a constant. It could be any combination of constants, but as long as all together as one, it is some constant value, then your value for the dependent variable is necessarily creating a cosine function, and the argument of the cosine function, the number inside the parentheses right before the t, is necessarily the square root of whatever constants you had in the differential equation. Like, it's a mouthful, but what I'm trying to say is this thing right here. On Wednesday, we found out that omega was the square root of k over m. K over m was the constant in the differential equation. Now what I'm telling you is from here on in, that's always true. The omega will always be the square root of what's inside the parentheses. Pause for a second. Like, I don't know. I think this guy. Oh, thank you. Okay, wait, sorry. Oh my gosh. Oh, thank you. Okay, sorry, quick pause. Someone just in the direct chat is totally paying attention. Just noticed that I uploaded, I made a slight, I made a typo in the upload for the game turn tonight. I totally appreciate that. I'm just going to fix it right. I mean, I know I'm like, yeah, but also, so I'm going to fix it right now. Thank you. And you could put in for points for pointing that out. And thank you for paying attention. But I'll also, I want you to think for a second what I just said, not just that person, the whole class. And yeah, you're right. It should be turn 8. Thank you. See if of course, it'll be more concrete when we do practice with it. But see if what I just said means anything. That's why I looked in the chat. Okay. Oh, you're welcome. Okay, thank you. Okay. I mean, okay. I know I have to do more concrete examples. Again, I will. But again, in a way, what those concrete examples are homework 2 and 3. Before I get to concrete examples, well, no, I'll do one super quick one, just like right now. If you're really if you're still with me, and obviously at least one person is, I'm going to do is like a super, like almost dumb exercise right now, just to try to make this concrete. But if you're paying attention to what I'm doing, you will see that what I'm doing, in effect, is just homework 3 with different numbers. Okay. So if you could follow this, it'll help you with homework 3 if you have not done homework 3 yet, which of course most people have not, and that's totally fine. So your quick and dirty example of what I'm saying. At least part of what I'm saying. Yep, sorry. Okay, say this is a total, just random example, just to try to make my point clear, okay? And again, I think it's essentially is homework 3, but different numbers. Say you're, excuse me, say you're walking down the street and someone just presents you with this differential equation. d2q over dt squared equals negative 625q. Now, like, right, or more reasonably, say you're in the lab and you're taking a bunch of data of how q relates to time or varies in time. I'm intentionally just saying Q out of nowhere. If you're still with me, you'll understand that I'm just using Q as like a random new variable. What does it really mean in the end? It usually means charge. It means amount of charge in something, which we will ultimately care about in this class, but I don't care for the moment. Just say Q is some dependent variable that you're measuring in the lab. If you know that you have this differential equation, if you know that Q produces data that suggests or forms this differential equation, right? Or if you have some independent like physics laws that lead you to believe that it obeys this differential equation, then what you immediately know, what I'm saying is then you would immediately know that Q is oscillating harmonically in time. You'll know that Q, its value is going up and down and up and down and up and down in the manner of a cosine function. Okay. And very specifically, you'll know that, and say the initial value of Q is five units, whatever they are. Then you'll know that Q equals that initial value of Q naught times cosine of omega t. Sorry, I'm running out of right. Like that's which is describes meaning Q is going back and forth in some cosine fashion. And specifically, the key point I'm trying to make right now is you'll know that omega, that rate at which the cosine is wiggling, in effect, the number of humps per unit time in the cosine graph, you'll know right away that that would be 5 radians. No, you won't. I'm totally kidding. You would not know that. You would know close. You would know that it would be 25 radians per second. Right away, you would know that the rate, the oscillating rate, the angular frequency of that cosine function would be 25 radians per second. Where did I get that from? Literally 100% simply because 25 is the square root of 625. What I'm just trying to drum in right now is for all of this conceptual hard mathematical work that we've done, in a way, a big takeaway that we're arriving is from now on, if you have a differential equation of the form second time derivative of dependent variable is directly proportional to the negative of that variable. I keep saying it slightly different ways to get you used to it. But if you have this kind of differential equation, i.e., second derivative equals negative times a constant times that variable, then you right away know that variable is oscillating cosinusoidally, which we're from now on going to call harmonically, and you know that the rate of the cosine graph is the square root of the constant. That is my big takeaway. It's a big takeaway because once you know it, it really simplifies life a lot. If you think that what I'm saying, if you're saying it all, if your brain is at all going like, oh, that's all he's saying, just like 25 is omega because 25 is the square root of 625. Yes, that is like literally what I'm saying. Just like 4 days ago, we found that omega was the square root of k over m because k over m was the constant in the differential equation. I'm saying that is a takeaway from now on in general. Okay, and please pause me. Oh, wait. Oh my God. Okay, I'm seeing the chat. I think is wackadoodly-doo. Hold on. Oh, funny. Okay, fair enough. And it is funny. It is funny. And it makes me love this class. I'm going to keep going, but yeah, don't push them at the track. Okay, yeah, you could cry. Yeah, whatever. Okay, very funny. And I will open up a portal for cool jokes that make me love you but that I can't afford to spend the time on at the moment. Remind me to open that portal. But yes, but I'm also going to take it since people are making jokes in the chat, which again, I do appreciate. I think it helps. But since you might also want to put in the chat if you're sort of getting what I'm saying or not. Because now what I want to do, like what I'm saying right now is, yeah, from now on. So, well, yeah, I'm saying from now on, if d2z equals, if d2z dt squared equals negative well, I'll write it one more time. I'm going to write it one more time. Thus, in general, and again, I'm telling you, you'll know. You also, if you're getting bored, if you're like, yeah, I get it already. Like you actually could make jokes for all the amount of time you're spending on this Yav round. If you're feeling that way, which I sympathize, you might want to like take a peek over to homework 3, the first couple, and see now if it makes a little bit more sense than it might have when you first looked at it. Like, hopefully you'll see that this is, the pro tip for homework 3. What I'm saying in general is this. And notice I keep writing it in slightly different ways because you'll see it in slightly different ways all over the internet and blah, 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 blah. But if you get what I'm saying, you won't care how it's written. And then what does it mean to get what I'm saying? I mean, you want to start recognizing this differential equation, the form of it. The form is second time derivative of some variable equals negative times constant times that variable. You shouldn't be thrown by what that variable is. I mean, you ultimately want to be not thrown by what they call that variable. And you also want to be not thrown by what the constant looks like. You want to be able to just recognize the difference between independent variables, dependent variables, and constants. So for example, I'm going to write it a slightly new way now. I'm going to say like this: if from now on you see this, which you will all over the internet, for example, and don't get me wrong, some of my best friends totally live on the internet. No, what? I don't know. I'm saying this from now on. You will often from now on you will see something like that. D2z dt squared equals negative omega squared times z. Z is any variable, right? Any dependent variable, any measurable dependent variable. T is time. Oh, wait, like lowercase t is time. So all of this all has to do with time. If the independent variable is not time, then we're in a totally different discussion. But as long as the independent variable is time, and as long as the dependent variable relates its second derivative to a negative times what I'm now from now on, notice from now on, I'm just going to write that constant as omega squared, because from now on, I know that the square root of it is what we call omega. So it's like a little Monday morning quarterback. Like you wouldn't understand this if this would just come but I'm saying if it just came out of you from nowhere, back to the street thing. But I'm saying from now on, we can write that constant as omega squared, because which is still a positive number and it's still a constant. It's not a variable. It's a constant, omega squared. Why we could have written it as C for constant, but we're writing it as omega squared from now on because we know in advance that the square root of it is what we call omega. So from now on, this differential equation is the differential equation for simple harmonic oscillation. Again, I'm going to get, and anything that obeys this differential equation is a harmonic oscillator, whether it's a mass on a spring or a pendulum on a string or a certain kind of circuit or something like that, or a temperature system. If it can be described by this differential equation, then it can be solved by this expression. And this expression says that the variable will oscillate harmonically in time at a rate of omega, for which omega is the square root of that constant. That's what I'm saying from now on. I still have more to say, obviously. Hold on a second. Okay, I'm just changing the view. Now let's say, okay. That's what I'm saying from now on. Oh, and so I'm really saying anything that obeys this math will behave in every way like a mass on a spring. It'll obey all of those things from homework 1B, including conserving energy. Okay. So anything that obeys this math will mathematically, precisely behave just like a mass on a spring in all respects, including energy conservation. Now, I want to, so I'm making a big deal. I'm saying omega is always the square root of those constants, of that constant, but like, what does that mean? I'm not assuming we're totally comfortable with omega yet. I'm just saying this. So let's try to get more comfortable with omega. So now, again, if there were anything to memorize about omega so far, you wouldn't memorize. I mean, you can memorize that omega square root of k over m, but please, hopefully, you're starting to notice the pattern, especially since you've had like 3 labs at least. It's not that omega always equals the square root of k over m. It's that omega always equals the square root of whatever the constant is in the differential equation. In the case of an m and a k, in the case of a mass on the spring, yeah, omega equals the square root of that, square root of k over m. But as you saw, I think, in one way or another with a pendulum, omega equals the square root of g over L, you might have noticed or seen, or you'll see again. Omega always equals the square root of whatever the constants are in the differential equation. So, but what does it mean? Like that's what a double equal sign. What's the triple equal sign of omega? Here's what it means. Okay. Omega stands for angular frequency. We said it's the letter we're using for this concept called angular frequency. Angular frequency means frequency of angles, rate at which we're like sweeping out or traversing, covering, completing some kind of angles. That's what omega is measuring, the rate at which we complete angles. But and it's measuring it from the start. The one thing we ever knew, the units of omega from the start have been radians per second. Like that's why we're calling it angular frequency, because it's like rate of radians. And radians measure angles. But where the heck are angles in this oscillating system? Like if a mass is going back and forth in a straight line, how is it that we're talking about angles or thetas or radians at all? It's a very good question. And like all of the questions, I feel like it's like really good to admit the confusion of that. If you've consciously wondered that at all, you're in the right place and I'm about to address it. If you've whatever hope, but if you haven't, like stop and think for a second. Like don't just accept this as memorization. Omega measures angular frequency. That's got to mean something. Where are the angles in something that's going back and forth and back and forth? Here's where. The first point, and I like everything else. You don't. Okay, very funny. I'm looking in the chat. You can't have too many points in this class. So you anyway. Challenge accepted is all I'm saying. What is an angle? Now, here's a very okay. Again, I swear, what I'm about to tell you, I don't think I realized until I was 40 years old. Like I had already been doing math and physics like for a while. Okay, angles and radians and cosine and sine and trig. One of the main reasons all that stuff gets a lot of us in trouble and sneaks up on us or bores us to tears, it just seems like a mess, is because it's all about angles in the end. And there's a fundamental misconception that many of us carry around about angles. For the longest time in my life, I thought this was an angle. I mean, it is an angle, but I thought this was the right way to think about an angle. It's not. What I'm saying is an angle is not a vertex between two lines. If you want to talk about how big an angle is, yes, at some level, maybe you're talking about, if you want to measure angles, at some level, you're talking about like why this is bigger than that. Yes. But what sort of, but only sort of. The mistake is thinking that when we're measuring angles, we're measuring like somehow like the space between these two lines compared to the space between those two lines. That will get you into trouble. That got me into trouble fast. Because first of all, like if you just want the space between these two lines, if you just want like how far apart they are, like in drawing a straight number of centimeters from one pen to the other, well, then you're just talking about distance and you don't need all this garbage. You might as well just have a meter stick. If you're talking about something a little bit more subtle, like how much they open up from each other in sort of a curve, which gets closer to the idea, then it gets closer to the idea, but then you start wondering like, wait, what if I measure here, I get one big thing, but if I measure here, I get a smaller thing. So how do I know how to measure how far apart these two lines are when I'm talking about angle? Here's the deal. What an angle really is not a vertex between two lines. What an angle is a fraction of a circle. That is what an angle is. When you say that one angle is bigger than another, you're saying it takes up a bigger fraction of a circle. Think about that for a second. You'll see what and I literally mean fraction, as in portion, but as also as in unitless. Hold on. And do I ultimately mean something like the unit circle? Sure, I ultimately do mean the unit circle. And yes, ultimately, I love the unit circle, and I think it helps me a lot with sines and cosines and trig and all that. But don't even worry about that yet. If you don't like the unit circle, don't even worry about it yet. You don't have to think about unit circle. Just think about a circle. Well, okay, just think about a circle. When we talk about an angle, like the thing is, don't just focus on those two lines. Focus on them in the context of a circle. Back up and say, and like, let me say this, for example. Felix, right, who many of you know, my 9-year-old, right? He doesn't know trig. He doesn't know sines and cosines yet, but he knows what a 360 no scope is from Fortnite, right? You better believe he knows what a 360, I don't even understand, but he knows what a 360 no scope is, right? He knows that a 360, and maybe some of you don't, he knows a 360 is going all the way around, starting at a certain orientation, doesn't matter where you start, but then going through a full circle and ending at that same orientation, right? That's what a 360 is. And everybody in this Zoom room knows what a 360 is. Now notice a couple of things about a 360. And that happens to be what we call degrees. And you're used to degrees, but you're just used to them. Don't worry about, like, what you know is that when you picture a 360, you're picturing going all the way around, and two things. You don't care where you start as long as you end up back at where you started after having made a full circle. Also, you don't care how big the circle is, right? I could hold my arms like this and do a 360, or I could hold my arms like this, whatever, and it's still a 360. Felix can recognize a 360 no matter how big the guy is that does the 360. That's how wide the guy is or the woman, and that's really important. Furthermore, Felix, and I'm just using him as an example, of course, but without caring about sines or cosines or angles, he doesn't think he cares about angles or sines or cosines. He knows what a 360 is, and therefore he totally also, as all of you, okay, you also know what a 180 is. It's a half circle, right? Everybody knows what a 180 is. It's do a half circle. Doesn't matter the size of the circle. Doesn't matter where you start. It means do a trip and don't come back, right? That's what a 180, I mean, you know what I'm saying, about face. Let's take it one step further. Everybody knows what a right angle is. Everybody knows what a right angle is. It's very hard to describe. It's like, oh, when the two things are like the same, when it's not like this and it's not like this, this is a right angle, right? Everybody knows. Now, it doesn't matter whether you call it a right angle or you call it 90 degrees or you call it pi over 2 radians, or you call it what the Greeks just called it, which was none of those things. They just called it a quarter circle. That's what it is, right? Everybody knows a right angle because it's half of a full circle, and everybody can recognize it. Whether you think you're thinking that or not, Felix knows that a 90-degree turn is don't do a full circle, don't do a half circle, do half of that. Just turn your, right? And it doesn't matter what measuring system you're using. And furthermore, the real important thing of a right angle is what really everybody knows about a right angle is it doesn't matter how long my two arms are. It doesn't matter the radius of the circle you're picturing. It doesn't matter how big the circle is. It's just literally a quarter of a circle, right? That's what, so an angle, first of all, okay, no, thank you. I see something in the direct. No, and I appreciate it. And honestly, the reason I'm yelling, and I hope that's true, like someone saying this is like helping them a little bit, which and like, again, I'm telling you, this didn't sink in with me until I'd already been teaching this for years and years. There's something about this. I don't know why it gets lost to all of us in translation when we first, but okay, good. I'm glad. Now here we're going to go a couple of steps further. Maybe why this occurred to me. The whole thing is then what all circles have. Well, okay. So wait. So I don't know which to say first. So it's just a portion. It's just a fraction of a circle. An angle is a fraction of a circle, no matter what numbering system you use, or whether you use degrees or units. Okay, quick thing also. Degrees, we all think we understand better than radians. All of us, including me, of course, I learned degrees before I learned radians. And by the time I learned radians in math, it was like very abstract and weird. But you got to understand that the reason we all, including Felix or some of us in the room or me, the reason we all think that degrees make more sense is just because we learned them first. It's just because we're used to them. Like, honestly, when I'm using Felix as an example, and then some of you don't know Felix, I'm just using little kids as an example to get this point home that Felix is comfortable in his mind that a full circle is 360 just because they say that all the time in Fortnite, right? So or in other places. So it's gotten into his mind. So he accepts that we divide the circle into 360 parts for whatever reason. He's never questioned it. It's just a habit that he's perfectly comfortable accepting. If you started thinking about it, you'd realize that why the heck do we divide a circle into 360 parts? We could divide a circle into any number of parts. And if you thought about it long enough, you'd realize actually that the reason that we divide a circle into 360 parts is honestly, I'm not going to pause to ask you, you might, that's funny, Michelle. The reason we divide the circle into 360 parts and call them degrees, or as opposed to dividing the circle into degrees, but making only 12 of them or something, is that for every one big 4-season circle that the sun makes around us in the sky, or that we make around the sun, for every big one sweep from the first day of spring back to the first day of spring that we perceive the sun to make around us, or that we make around the sun, what you now know, what happens is for every one of those big 4-season cycles that we call a year, there's approximately 360 sunrise, sunset cycles. Like there's approximately 360 of these in one of those. And I promise you, that's the reason. And they chopped it off to 360 because it's much easier to use. 360 is divisible by 10 and 12 and 5 and 4 and all these. So they took the 365 that's in the sky and they imposed it onto, and it turned it into a 360 into the circles on like our pieces of paper. And in some ways, for people way back then who actually understood that astronomy is the basis of all physical sciences, it did make some historical sense to graft that big seasonal circle onto the circles that we're dealing with on our piece of papers. But I'm just telling you that and I think that's fascinating, I do. But like, I'll be darned if any one of us is ever, when we're doing circles or playing Fortnite or whatever, none of us is thinking like, oh, 360, that makes sense because there's like almost 365 days in the year. Like, frick no, right? It doesn't make sense to us. The universe, I mean, the outer space is not helping us do geometry in a video game. It's just the historical. What I'm saying is, don't fool yourself into thinking 360 makes sense. It doesn't make sense in any helpful, direct way. It just makes historical sense. what makes sense is the recognition that it doesn't matter how big the circle is you take, the fraction of it is still the fraction of it. And so what we do is we say an angle is how much we take of the edge of the circle per the size of the circle, meaning just this. Oh, sorry. Meaning, yeah, sorry, okay. All right, sorry, I started, but it all does come from us. But anyway, meaning this, and I know you've seen this in math, I'm just trying to put it in perspective now. What an angle is how much of a chunk of a circle you take. But so you could just look at it as like, how much of the crust of some pizza have you taken? Like, the more crust you get of that pizza, the bigger angle you've taken of that pizza, right? But we don't want to measure in meters. We don't want to say, aha, I've taken 12 meters of arc length around the crust of this pizza. Because if we just leave it at that, if we just say, well, the more crust you take, the bigger fraction of the circle you've taken, that doesn't take into account the fact. Wait, okay, wait, just easy for a second. I love, okay. What I'm saying is, it's how much crust you get per, it's how many meters of crust you get for a given circle per every unit of radius that circle has. In other words, an angle, in other words, I'm saying, just like when you try, if you want to measure, if you want to say this is a right angle and you want some way of measuring along an arc length from one of my hands to the other, we all recognize that you're going to get more arc length if you measure farther out. So we just agree in advance. Well, let's just say you go 1 meter out on my hands and measure the arc length to the other hand. As long as you go 1 meter out, whatever answer you get, that's what we mean by a circle. If you happen to have hands that are 2 meters long, then whatever answer you get, divide by 2 to normalize it so that we're using the same base for all of our. So I'm saying in the end that an angle is a pure fraction. It's a ratio of meters to meters. The meters cancel out. In other words, it's arc length to radius. The meters cancel out so here's my key point and my key example of this. This is what an angle is measured in radians, right? Such that if we go around a full circle, so again, I'm saying angle is fraction of circle. The way to picture a fraction of a circle is just picture how much of the how much of the circumference did you cut out of that circle? But then divide that by the size of the radius so that we're all, so we're not getting thrown off, so that we're not getting bigger fractions mistakenly just because we have bigger circles. I hope that sort of makes sense, but here's an example. Here's the key example of it. I'm saying if you go around a full circle, and want to know what to call that angle, well, yes, historically we call a full circle 360 degrees, but that's all that is. That's history. And astronomy, which Katie doesn't like anyway, right? I mean, but really, historically, astronomically, when we go around a full circle, we call this 360 degrees. So we got used to it, but it doesn't literally make direct sense. There's no law that says we should divide the circle into 360 parts. How many parts should we divide the circle in? Well, look at it this way. If we go around a full circle, but explicitly, if we're explicit about it, if we go around a full circle, the arc length around a full circle, in other words, the full circumference of a circle, is always 2 pi times the radius, 2 pi r, right? And then according to this definition, if we divide by the radius, the radii cancel, and we get 2 pi, what am I saying? I'm saying two things. I'm saying two things. I'm saying, why does pi suddenly come into our lives? Why are radians always have why are radian measurements of angles have pi's in them? Why is the total angle around a full circle known in Fortnite as 360 degrees, but known in a math class as 2 pi radians? Like, what is that? So it sounds so intimidating and so out of nowhere, but no, what pi is this very notion that the ratio between going around a circle versus going straight across it is always a constant, regardless of how big that circle is. The important discovery about circles that makes them so important. The important discovery about circles is not whether the number is 3.14159 or 3.15. It doesn't, forget the value of it for a minute. The issue is that if you go to any tree in the forest, and you wrap a string around that tree and you put the string down on the ground, and then you take another, and then you cut straight across the tree and put a string straight across it, right? So one string went around the tree once, and one string went straight across the tree. You put those two strings down on the ground, the one string will always be just a little bit more than 3 times as big as the other string, regardless of how big the tree is. That's the importance, that the ratio of the circumference to the diameter is a constant for all circles. That's not obvious. I wasn't born knowing that, and it's not true for other shapes. It's true for circles, that the ratio of going around to going across is always the same, and that same ratio we call pi. So, according to the definition of so going back to this, so number one, that's why pi comes into the discussion, because the discussion is about fractions of circles. The best way to express a fraction of a circle is arc length that you get per unit radius. Arc length measured in meters, radius measured in meters. The meters cancel out. We're looking at pure fractions here. Angles are literally dimensionless fractions, right? And they're measured in units of pi. I mean, they're measured in no units, but they're measured in multiples of pi, because pi is that multiple that dictates how far you have to go around per every unit that you have to go across. So, from one takeaway I'm saying right now, I'm yelling, so it's got to be important, or I've got to be a crazy person, or both. What I'm saying right now is, excuse me. Yep. From now on, a full circle in our language from now on doesn't equal 360 degrees. Like, you could say that, but what we could also say from now on is a full circle equals 2 pi radians. 2 pi is the ratio of going all the way around versus going from the center out, right? I mean, it would be pi radians if it was ratio of circumference to diameter, but we've decided to make it circumference to radius. So a full circle is 2 pi radians. That's number one. Now, still, what does that have to do with masses on springs? We're almost there now. Here's where we are. We're looking at oscillators that we call harmonic, things that go back and forth and back and forth. They are going back and forth. They're going back and forth. They're undergoing cycles. So what we're here to do is take the math and everything we said about this harmonic oscillator so far in homework 1. Part of the conclusion we're coming to is all these properties that it has are true about its cycles, regardless of how big its cycles are. One example of that is omega equals square root of k over m, right? Omega equals square root of k over m. Notice what was not in that equation. There was no x naught in the formula or the finding for omega. The rate at which the thing went back and forth had nothing to do with the size of the cycle it was making, had nothing to do with how far out the thing started. So we're making discoveries in physics about physical systems that are cyclical, and we're making discoveries about these cycles that seem to be independent or constant no matter how big the cycles are. So we take the math of circles, because the math of circles, particularly angles, works no matter how big the circle is, and we're going to graft the math of circles onto the physics of cycles. That's what's going on here. That's literally what's going on. Why cosines and omega and radians and all that is coming into play is because we're taking our mathematical understanding of circles and applying it to the physical understanding of cycles. And the reason it works is because the math of circles doesn't care how big a circle is, and the physics of cycles doesn't care how big a cycle is. That's what's going on. So now more specifically, from now on, a cycle from now on, a cycle. Oh, it's frozen. No, sorry. Why is it? Yeah. From now on, 2 pi radians equals 1 cycle, by which I mean 1 closed path, right? It's all back to closed paths. 1 closed path, meaning there and back. Like, meaning from now on, you don't have to see curves in what's going on. There don't have to be curves or angles or anything. Even something that's going in a straight line there and back is making a cycle. So from now on, when something goes there and back, we call that a cycle, and we say that that is 2 pi radians. Similarly, pi radians from now on, I mean, so this is just like 360s and 180s and all that, right? From now on, pi radians means a half cycle, et cetera, like pi over 2 radians means a quarter cycle, et cetera, right? And furthermore, pi is a number. Pi is approximately, just for perspective, pi is just a number. It's approximately 3. Well, it's approximately 3.14, but that's approximate itself, as you know. So just to picture all this, to make my life easy, pi is approximately 3. It's not exactly 3. Okay. Okay, thank you, Shawnee. Okay. It's approximately 3. So and I strongly suggest that you hold that in your mind, just like we hold gravity is approximately 10. We're not like getting a Nobel Prize with that value, but we're at least like picturing things correctly with that value. So if pi is approximately 3, then what I'm saying from now on is that 1 cycle is approximately 6 radians, like literally, not exactly, but literally from now on. When I picture a cycle, I'm going to picture 6 radians, or put another way, if you say to me from now on, wait, what is it? If we're talking about omega, and omega, right, is in radians per second. What omega means is how many radians are being covered by this mass on this spring every second. And at first, if you bump, you're like me. When first I hear that, I'm like, the omega for this mass on a spring is like whatever, pi over 2 radians per second, or 1.5 radian. Like, where are radians in all of this? What I'm here to tell you from now on is, if you're ever asking, wait, what is a radian? You know what a radian is? Literally, what 1 radian is from now on is literally, approximately, but literally a 1/6 of a cycle. Like, literally, in my mind, when someone says radian, especially in a physics context, what I think is 1/6 of a cycle. 1/6 of a cycle. How big is the cycle? I don't know. I don't care. That's the whole point. Whatever I'm going to say about radians is going to be true regardless of how big the cycle is. But a radian is a 1/6 of a cycle. Why a 1/6? Because 6 is 2 pi. So approximately. Again, I'm just trying to picture things. So if someone says to me, that thing has that mass, that oscillator has an angular frequency of about, if they say it has about 6 radians per second, or if they say it has like like about, if they are more exact, and they say that has an omega of 2 pi radians per second, what that really means is it's doing one full trip, one cycle per second. A radian is just a sixth of a cycle. If you want to convert it in your mind to something that's a little bit easier to picture, or see, a little bit less mathematical, or a little bit more like real worldy, you're like everybody else. You can do that. If you want to convert an angular frequency into a what's known as a standard frequency, from now on we'll let F stand for standard frequency. Okay, standard frequency is not number of radians per second. Standard frequency would be exactly what you would think any normal person in the normal world would care about. The units for standard frequency would be just actual cycles per second. Okay. Now, right. And there's a name for that. One cycle per second in the real world, in the real world. One cycle per second, you may or may not know, or you may recognize as soon as I say it, one cycle per second is known as a hertz. So 1,000,000 cycles per second is known as a megahertz, like radio tuning, right? Like if you listen to, if you listen to NPR, for example, like 93.9, right? Now NPR is 93.9 megahertz on your FM dial. What are they saying? They're saying something vibrates at a frequency of 93.9 million cycles per second on your FM dial, your frequency modulator dial. When you're dialing, you're modulating, you're changing the frequency with which something that happens to be an electromagnetic wave, which we'll get to by the end of the class, is vibrating, oscillating. Okay, so frequency is measured in hertz or kilohertz or megahertz or whatever. A hertz is a cycle per second. If you want to get from this mathematical way of thinking to the sort of more typical, that's funny. That is funny. Okay, noted. But yes, thank you. That's actually so funny. I'm totally distracted. Okay. If you want to convert back and forth, the conversion factor is just simply that there are 2 pi radians per cycle. In my mind, that it means 6. But if you want to be exact, you could say 2 pi. In other words, F by definition is just simply omega over 2 pi, right? It's radians per second divided by radians per cycle. The radians cancel and the cycles flip up and you get cycles per second. Last thing, I know we have 6 minutes, by the way, right? Last thing, and I'll put this all together again. I'm just trying to relate back to things that were coming up in lab. I know for weeks, they never make sense at first when they come up in lab, because what's coming up in lab first is not sense, it's data and experience. And now we're trying to make sense out of it. It's like physics. But I'm saying that sympathetically. But so now what I'm saying is frequency in the real world, standard frequency measured in hertz, is simply the reciprocal of the thing that is easiest of all, or most straightforward of all, for all of us to measure in the lab and relate to in our minds. And that is capital T, which stands for period, right? As in the thing that you measured in lab 2 a lot, or lab 1 a lot. Period of time, right? The period for one full cycle. That's what capital T means, the amount of time it takes some oscillating system to complete a full cycle. So the units of T, whenever I use square brackets, I mean units, right? The units of capital T are seconds per cycle, whereas the units of capital F were cycles per of lowercase f were cycle per second, and the units for omega were radians per second. So in sum, what I'm saying right now, really quick, we have 4 minutes, and then this again, I swear, if you even want to skip to homework 3 first and look at it, you'll see I'm essentially telling you exactly what you need for homework 3, and then you can go back and fill in homework 2, if you, whatever. But what I'm saying is this. If someone comes along and says that the omega of this oscillator is 2 pi radians per second, well, it sounds really obscure when you first hear it, but all they're saying is that the standard frequency of it is 1 cycle. Here, let me be more specific. Sorry, say they say 4 pi. Sorry, say they say 4 pi radians per second. Then all they're really saying is that the thing does 2 cycles per second. It goes there and back twice in every second. If they say 4 pi radians per second, that just means there and back twice every second. And what that just means is that it takes a half a second to do every cycle, right? If you're following me, and I know we have 3 minutes, I'm literally saying 3 interchangeable ways to measure cycling rate, 3 interchangeable ways to measure cycling rate, which is what we're all about here now. We don't care about the size of cycles. We care about the rate at which cycles are performed, right? If you know one of these, you automatically know the other 2, because I just linked them all together, right? I mean, you could put them all together if you like this. Some people will put them all together in one equation like that. If you like whatever, if you know one, you know the other 2, you might say, well, then why do we need all 3? Because T is the one that is the most directly measurable and picturable for everybody, no matter how advanced we are. Period is what you can literally measure in the lab, and that's what you're doing in at least the first 2 labs. Omega is what comes directly out of the math. Omega is what comes out of the differential equations and the cosines and all that. So omega is the most strictly analytically powerful. T is the most experimentally accessible. F, standard frequency, is the bridge between the 2. Okay, so that's where it's at. And the last thing, so in the end of the day, at the end of the day, when we say the thing that I started with is, when we say, for example, this, oops, sorry. Right, at the end of the day, to find out that x equals x naught cosine omega t and omega equals square root of k over m, the big revelation in finding that out is we're saying the cycling rate for that oscillator depends fully only on the constant material properties of the system K and M, what we're from now on going to call parameters. I'm saying, and I will start the class on Wednesday with this conclusion again, but I'm saying, at the end of the day, when we say omega equals square root of k over m, what we're saying is, if you know the stiffness of the spring and you know the size of the mass, and you put them on the even before you assemble your mass on a spring, if you just know those ingredients, you automatically know the rate at which these ingredients go back and forth, regardless of how you set up the system, regardless of the amplitude, regardless of the initial conditions. If you know the ingredients, you automatically know the cycling rate, and that's what we really mean by harmonic. A harmonic oscillator is an oscillator whose rate of cycling is constant and fully determined by the ingredients of the system. That's 130. So I will repeat that on Monday, of course, but that is the point of all of this. Okay, you've been very patient as always. Quark, bless America. You just do whatever you're next in the homework. Hopefully find it's getting easier and easier. Just do wherever you're next. I'm going to sit here in case there's any questions or anything, but I'll see you Wednesday. Yes, goodbye. Thank you. Goodbye. Have a great day. I'll turn off the recording, blah, blah, and I will shut up.